So, the easiest way to go about this is to learn the set of polyatomic ions. This would be like nitrate ion, or ammonium ion, or sulfate ion. Learn those as they're given in table 2.5. Those are the ones you're responsible for. And then we put together the formulas in the same way that we did before. That is, we use the formula of the anion and the formula for the cation. So calcium nitrate would be calcium 2 plus, as calcium always is in ionic compounds. And then nitrate ion has a single negative charge. I learned that some time ago. And therefore the formula is calcium. Nitrate in parentheses now, must be parentheses if it's a polyatomic ion, and there's two of them there. Question, fixed numbers of water molecules. Now, what this means is, let's suppose you prepared one of these compounds in the laboratory, and it crystallized out of water, out of aqueous solution. The crystals would have in them not a variable amount of water, but a fixed amount of water. An example is a material called Epsom salt that is kind of a common material around pharmacies and things like that. It is magnesium sulfate dot 7H2O, meaning associated with every formula of this compound there are 7 waters. To name it, we name the ionic part, which would be magnesium sulfate in this case, and then we say how many waters there are and the word hydrate to indicate its water. So magnesium sulfate heptahydrate, hepta being the prefix that specifies 7. Now table 2.6 has a list of these prefixes that you need to become familiar with. I don't think you'll have any trouble with that. It's pretty common. Di, tri, tetra, penta, so forth. Okay, so if you run into a hydrate, that's how you name the hydrate. Now I've put in an exercise right here, and I want to do this to kind of help you focus. I assume that since we talked about table 2.5 last time, some of you have looked at this. So here's a little workshop. What, if anything, is wrong with each one of the following names or formulas? You don't have a slide on this. I just want you to think about it. The acetate ion, in case you haven't learned it, has a formula C2H3O2, and it has a single negative charge. So this states that Ca, C2H3O2 taken twice, is called calcium diacetate. Is there anything wrong with that? What is it? The di. The di. We don't have to say it. The calcium having 2 positive charges and the acetate having 1 negative charge is enough to write the formula. So calcium acetate, not diacetate. Okay? All right. Let's look at another one here. In fact, let's put them all out here, and then I won't have to go back and forth. Lithium sulfite has the formula Li2SO3. Is there anything wrong with that? Be careful. What charge is on lithium? +1, right? Lithium's in group 1A, so the lithium ion has a single positive charge. What charge is on the sulfite ion? It says sulfite. -2. -2. So 2 lithiums per 1 sulfite gets the charge right. But there's still something wrong. The parentheses. I heard someone say it. The parentheses. You don't use parentheses with monatomic ions. You don't have to. Okay, so this should just be Li2SO3, no parentheses. Questions on that one? Okay. Iron 2 phosphate has the formula Fe2PO4 taken 3 times. Is there anything wrong with that one? Okay. Iron 2. Is this iron 2? It's not, is it? Why not? Because phosphate has a charge of what? Negative 3. Negative 3. PO4, 3 minus. So, 3 of those would be 9 negative charges, and that's certainly not equivalent to iron 2. So the 2's and the 3's are mixed up here. This would have to be a 2, which would give 6 negative charges. This would have to be iron 3, iron 2's. Okay? Iron 2 phosphate ought to be Fe3PO4 taken twice. Does that make sense? Anybody have trouble with it? Okay, let's look at the last one. Cesium carbonate has the formula CS2CO3 in parentheses. Is there anything wrong with that? Is the charge right? Carbonate ion has what charge? Negative 2. Carbonate ion's negative 2, CO3, 2 minus. Cesium has what charge? Plus 1, so it's going to take 2 cesium, so that looks right. So the only thing that's wrong here is the parentheses. If there's only one of them, you don't use the parentheses. Only if there's 2 or more. So we would take out the parentheses. It would be CS2CO3, and that would be right. Questions on that one? Okay, so you have some inkling about the kinds of things that can be wrong with formulas. In the polyatomic anions, oxoanions are the largest subgroup. And an oxoanion is just an element that could be a metal or a nonmetal that's bonded to one or more oxygen atoms, and if they're an anion overall, then it's one or more negative charges on it. So nitrate ion would be a good example of this, carbonate ion, and so forth. The naming of these things is a little bit more complicated in that sometimes the oxoanions exist in families, and we have to have some naming that will tell us what family we're in. Okay, so the families of oxoanions, as it says here, are different in terms of the number of oxygen atoms. To talk about this, suppose there are only 2 oxoanions in a particular family. They're almost all 2 or 4. I can't think of one offhand that's other than 2 or 4, or in some cases it's 1. But if it's a family of 1 is hardly a family. So the ion with more oxygen atoms takes the nonmetal root and the suffix ATE. ATE means more in this case. And the one with fewer oxygen atoms takes the same nonmetal root and the suffix is ITE. To illustrate this, all we have to do is look at sulfate, SO4 2 minus. You probably already knew that. And sulfite, which is SO3 2 minus, as we saw in our example, our little exercise a while ago. So 8 more oxygen atoms, 8 less oxygen atoms. There's a similar thing with nitrate. NO3 minus is nitrate. NO2 minus is nitrite. 1 fewer oxygen atoms. Okay. I would like to take this to the other possibility of there being 4 oxoanions in a family, and there's only a handful of these that we might run into. When there are 4, we use both prefixes and suffixes to name the oxoanion. And again, we separate these things according to the relative number of oxygen atoms. The one with the most oxygen atom is given a prefix per and the nonmetal root followed by the suffix ATE. Per something ATE. The one with one less oxygen atom than the most has no prefix, and it keeps the suffix ATE. Okay? All right? The one with 2 less oxygen atoms doesn't have any prefix, and it it has the new suffix ite. So this is sort of like the two anion family. ATE and ITE works the same way. The one with less oxygen atoms is ITE. Finally, the one with 3 less oxygen atoms is given the prefix hypo. This is one of the only places you'll see hypo in a chemical name, at least of inorganic compounds, and then the suffix ITE. So let's look at the chlorine oxoanions, and you'll see examples of all 4 of these. This is the best known family of 4 oxoanions. So we'll start with the one with the most oxygen. It's ClO4 with a single negative charge. So it is per, there's the prefix, chlor, there's the root, ATE, there's the suffix, perchlorate. All right, so if you see a description of an oxoanion and it's called perchlorate, you'll know it's ClO4 minus, if you remember this, and you should learn it. If there's one less oxygen, ClO3 minus, notice the charge is the same, then it will be chlorate with no prefix. Okay? It just drop the prefix when you drop one oxygen. If you have ClO2 minus, drop one more oxygen, then you change the suffix to ITE. So ClO2 minus becomes chlorite. Chlorite. Chlorite's not a very common material. Perchlorate and chlorate are both common. Finally, with one oxygen atom, ClO minus then uses the hypo and the ite to make this hypochlorite. So that's the system of naming of oxoanions in 4 families of 4. Does anyone have a question on that? There's nothing for it but to memorize it. Okay, it's arbitrary, so you have to memorize it. You can't figure it out. Okay, then I've got another problem or exercise to work on here. Give systematic names for the formulas or formulas for the names of the following compounds. Fe, ClO3 taken twice, sodium carbonate, BaOH taken twice, dot 8 H2O. Right? So let's start with this one. ClO3 minus we just looked at. What's its anion name? Chlorate, isn't it? And what charge did it have? -1. So 2 of them would have -2, so this must be iron 2 chlorate. Notice it's not iron 2 dichlorate. That's redundant. Iron 2 has all the information you need so that iron 2 chlorate would have this formula, FeClO3 taken twice. Okay, questions on that one? Good. Sodium carbonate, now we want the formula. We're given the name, so we want the formula. Now, carbonate ion is CO3 with how many negative charges? 2 negative charges. Sodium has a single positive charge, so it'll take 2 sodium ions to balance 1 carbonate ion, so the formula will be Na2CO3. It's not disodium carbonate. It's sodium carbonate. That's all you need to get the formula. Questions on that one? You see the pattern. Okay, the last one is one of these hydrates. It has 8 waters attached to a formula here. So it'll be named in terms of the formula for the ionic compound. In this case, it's barium hydroxide, and then it will have a suffix attached to it that says how many waters there are. So Ba2 plus is barium, OH minus is hydroxide ion. It has a single negative charge. It's on the table. If there are 8 water molecules, then the name will be barium hydroxide octohydrate. Why is it not barium dihydroxide or barium? Why is it not barium 2 hydroxide? Barium has only 1 charge. So it's not necessary to distinguish between the different charges of barium. Barium is in group 2, all of those ions have a single charge, and it's 2+. So barium hydroxide carries all the information that you need to write down BaOH taken 2 times. Assuming you know that hydroxide ion has a negative charge. The last part of it is octa for the 8 and hydrate for the water. How are we doing? Does this make sense? All right, good. Now we have to name some acids as well. And fortunately, most of the acids are named in a way that depends on the anion in the acid. Acids differ in the anions that they have. They all have hydrogen, but they have different anions. So acids are a type of hydrogen-containing compound, and to name them, we treat the acid as sort of an anion with enough hydrogens attached to make it neutral. Okay? This is bogus, incidentally, but it works perfectly well for the process of naming. As a general rule, we recognize 2 kinds of acids. The first kind is called a binary acid, and the binary acid would be something like HF or HBr. It would have hydrogen and only one other atom in it. Binary meaning 2 atoms. Okay? And then the oxo acids, and these are describable as being oxoanions coupled with enough hydrogen ions to make them neutral. So oxoanions plus enough hydrogen ions to make them neutral. So in the first case, gaseous hydrogen chloride, it comes as a gas, hydrogen chloride, dissolves readily in water, and when it does so, it forms a solution that the label on the bottle says is hydrochloric acid. If you go up and pick up hydrochloric acid, it was made, in most cases, by dissolving the gas, hydrogen chloride, in water. The name for binary acids consists of these parts. You start off with a prefix hydro. You only do that for binary acids. So hydro plus the anion nonmetal root. Okay? And in this case it's hydro. Chlor is the nonmetal root for chlorine. And then you add IC as a suffix to that, and then the word acid. So hydrochloric acid, you would read that to be a binary acid that has chloride ion coupled to 1 hydrogen. We know it's 1 because chloride forms a monoanion. Okay, so we'll name these things using this scheme. Hydro plus the anion nonmetal root plus IC plus the word acid. Now, oxo acid names are derived similarly, except there are 2 suffix changes that we have to use to deal with oxoanions. So we would take the oxoanion and couple it with enough hydrogens to make a neutral formula. And if the anion itself has an ATE in its name, like nitrate, sulfate, the suffix added on to the name of the oxo acid is IC. Okay? So if we were talking about nitric acid, HNO3, then you could view this as the nitrate ion plus a hydrogen ion to make a neutral structure. Okay? So this acid would be nitric acid. You would not use the word hydro. You would start with the root name of the anion, the nonmetal in the anion, add IC, and acid. If the anion has an ITE ending like chlorite or sulfite, then the suffix, instead of being IC, becomes OUS. Now, if the oxoanion has hypo or per prefixes, you keep them. Don't throw them away. If the anion comes with those, the acid will need them. So, if we look at a couple of examples, BrO4 minus is the perbromate ion. Okay, it's a member of a 4-member family. It has the most oxygen, so it's perbrom 8. So what we're going to do is we look at the 8, and HBRO4 will be the formula, and its name will be perbromic, A to E changes to ic, acid here. So HBRO4 is the formula, the name is perbromic acid. Is that clear? Okay, we're going to do one more, an obscure one here. Here's one you'll never see in your life, most likely. IO2 minus is the iodide ion. And you can see it has one negative charge on the iodide ion, and therefore it will take one hydrogen. So the formula will be HiO2, and since the oxo anion has an ITE ending, we change that to OUS. So this becomes iodous acid. It's a pretty unstable acid, but it illustrates the point. Questions on those? So now, yes? I'm naming the oxo anion here. I have to look at that, so I'm giving you the formula for the oxo anion, because the number of negative charges there tells you how many hydrogens to add. That's why I put it there. Other questions? Yes?
So, in the naming, the hydrogen is what matters. When the hydrogen comes in, that's when the name changes?
You're asking when do we apply these names? And the answer is yes. The acid must have the hydrogens there. That's the key element of an acid. So it's in that point. In other words, when we've reached the second line here and we've written the formula down, and you see the hydrogen there, and you see one hydrogen goes with one perbromate ion, it's then that you name this thing as an acid. So the answer is yes. Okay, other questions? Yes?
Yeah, so what if the oxo anion has a negative charge? Do you add 2 hydrogens?
2 hydrogens. He asked if the oxo anion has 2 negative charges, how many hydrogens do you add? You need to balance the charge. So if it's 2 negatives, you need to have 2 hydrogens to balance it. Sorry, went backwards here. So we now have a problem. Another example. I do many, many examples for you. I hope you don't get tired of them. At the end of the semester, I always have students who say, you didn't do enough examples. I think I do more than enough, but you'll see. So we want to name the following anions and give the names and formulas of the acid solutions derived from them. So Br minus will form an acid which has 1 hydrogen. So this would be, this is bromide ion. And bromide ion will form the acid HBr, and the name of that acid, since it's a binary acid, is hydrobromic acid. Hydrobromic acid. Number B here, IO3 minus, as we saw a few minutes ago, is the iodate ion. It's going to take 1 hydrogen to balance its charge. So this would be HiO3. And ATE ending of the oxo anion goes to IC ending for the acid. So this becomes iodic acid. Dr. Bott likes to call this an idiotic acid, but it's really not spelled that way. Okay. Okay, let's look at the next one, number C. Cn minus is the cyanide ion. And the cyanide ion behaves almost as if it were a halide ion. It behaves a whole lot like bromide ion. So cyanide has one negative charge. How many hydrogens will it take? One. So the formula is HCN, and the name is hydrocyanic acid. And when we used to use gas chambers to execute people guilty of heinous crimes, this is the stuff that did it. Questions on hydrocyanic acid? All right. Last one is NO2 minus. Somebody tell me what the name of NO2 minus ion is. Nitrite. Good, good. You're learning the acids. Learning the anions, I mean, and you'll be learning the acids quickly. So, nitrite has a single negative charge, and the formula of the acid then will be HNO2, and what will be the name of the acid? Nitrous acid. OUS for the ending. Questions on any of those? Whereabouts? Whereabouts? Still can't see you. Up, 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 up. Go. Go. Yes. The cyanide ion behaves like a monatomic ion. Even though it has two atoms in it, it behaves like bromide ion. So you treat it the same way as far as its acid goes. It's stretching a point, I admit, but it works. Okay. I beg your pardon? Only exception? It's the only one I can think of right now, but I have this sinking feeling that there might be another one or two around. If it's not in the table, you don't have to learn it. Okay? Let's talk about naming binary covalent compounds. Covalent compounds made up of two different kinds of elements, atoms, if you will. Now, there are some of these simple covalent compounds that have common names, like ammonia and water, for example. And we just use those names. We don't call water dihydrogen monoxide or some funny thing like that. We just call it water. Now, for other compounds, we use a systematic method for getting the name that has 4 rules in it, and they're going to be pretty familiar. The first thing we have to be concerned about in a binary covalent compound is what element to name first. The general rule is the element with the lower group number in the periodic table is named first. Okay? Now, the lower group number, of course, means furthest to the left in the periodic table. There is a major exception to that. Well, really, there's 2. Hydrogen is not usually named first, but we're going to have to treat its compounds separately because of the fact that it is a unique element. The more important exception is if a compound contains oxygen and a group 7 element, a halogen, fluorine, chlorine, bromine, iodine. We name the halogen first, even though it's to the right. And this is nothing more than an historical precedent. It's been done this way too long. They know that old chemists like me could never relearn it, so they're kind to us. Okay? If both elements are in the same group, then the one lower down in the group is named first. And the second element, then, once you decide who's on first, the second element is named with its root and the suffix IDE, just like it were an anion, even though it's not. These are covalent compounds. Okay. Last, we use numerical prefixes to indicate the number of atoms of each element in the compound. Now, the reason that we have to do that here, and we didn't do it in naming ionic compounds, is that there are no simple rules for determining what the connectivity of a nonmetal atom is in a covalent compound. So we can't just say phosphorus sulfide. There are a handful of different phosphorus sulfide compounds. So we have to say specifically how many phosphorus atoms and how many sulfur atoms. Well, that should make us breathe a sigh of relief. We don't have to figure anything out. If there's 4 phosphorus and 7 sulfurs, then it's tetraphosphorus heptasulfide. Okay, we have 3 problems, 3 questions here. Formula from a name, carbon disulfide. Is that a tough one? No. Pretty easy. Carbon, 2 sulfur, CS2. Carbon disulfide. IDE ending on the second element, and carbon's to the left, so it's named first. Okay. ASF5. AS is arsenic, and it's in the periodic table right under phosphorus. And so we're going to name it first because fluorine is to the right in group 7. Arsenic's in group 5, fluorine's in group 7, so we name it first, arsenic. And notice we don't have to do anything special with the endings or anything. We just name it arsenic. And then there are 5 of these fluorines here, and they will be named as pentafluoride. There's the IDE ending. Here's the nonmetal root, and here's the prefix that tells how many there are. Arsenic pentafluoride. Questions on that one? Yes?
Why is the ending IDE?
It's one of the rules of the naming thing. It tells you that that element is to the right somewhere, and it gives you a feeling for the difference in the chemical qualities of the 2 elements that make up the compound. It's not really an anion, but it's named the same way as if it were. Give the name and formula of the compound formed from 2 nitrogen atoms and 5 oxygen atoms. Well, if it has 2 nitrogen atoms and 5 oxygen atoms, we ought to call it dinitrogen. Why nitrogen first? It's to the left. It's to the left in the periodic table. Very good. Dinitrogen. Pent oxide. Now, it's not pentaoxide. You don't put 2 vowels together. If the second part of this thing starts with a vowel, you leave the A off. Although you'll see sometimes people write it different ways. But it should be pentoxide, like pent-up enthusiasm. Okay. Dinitrogen pentoxide N2O5. How's that? Yes? It depends. He asked whether if you had HF, you would call that monohydrogen fluoride. You would not in that case because of the naming of acids says that you have 1 hydrogen for each negative charge on the anion. Anion has 1 negative charge, so that tells you that it's 1 hydrogen. So you don't use mono. Okay. The only time you would ever use mono is if it told you something that the formula couldn't tell you. And I'll try to find an example of that sometime and point it out to you. I want to do some things about organic compounds for you, because we're going to use organic compounds in many of the examples that we'll use as we go along through the text. So your textbook has a small introduction to naming organic compounds, and it starts with hydrocarbons, which are just elements, just compounds that contain only hydrogen and carbon. So a hydrocarbon is some combination of some number of hydrogens and some number of carbons and nothing else. Okay? Now, there is a family of hydrocarbons, and they differ in the number of carbons present in the basic unit. The basic unit of hydrocarbons, since we have two nonmetals involved here, is ionic or covalent? It's covalent, isn't it? It's covalent, and carbon has a dependable characteristic that we can use in this, and that is it forms 4 bonds 99.999% of the time. 4 bonds. So we could take advantage of that. Hydrogen, of course, only forms 1 bond. So there are a series of hydrocarbon compounds called alkanes, and they are the simplest hydrocarbon compounds, and that family starts off with methane. Methane has a formula CH4. It is the simplest alkane and one of the simplest hydrocarbons. And you can see its structural formula here and here. Carbon in the middle, 1, 2, 3, 4 bonds, and that's the only way you can write it. The meth, METH, indicates there's only 1 carbon. And there is a series of these that differ in the prefix here, and we're going to want you to learn the prefix for the first 10 of them. Okay? Now, because of the way these molecules are put together, it's possible to generalize about the alkanes, and that is the formula for alkanes can be written down as CnH2n plus 2, where n is an integer starting with 1. So n could be 1 or 2 or 3, etc. So if n were 1, this would be CH, 2 times 1 plus 2 would be 4, and so that's methane. Okay? You comfortable with that? If n were 2, then it would be C2H, 2 times 2 is 4 plus 2 is 6, C2H6, and that would be the second member of the alkane series, as you see here. N is equal to 2 for ethane. And then the next one is propane, that has 3 carbons, and butane that has 4, and pentane that has 5, and so forth. So, learn the straight chain alkane names in table 2.7. I've given you the first 4 of them: methane, ethane, propane, butane. Now, sometimes alkanes are more complicated than straight chains. Straight chain means that we have, for butane with 4 carbons, it would look like this: C, 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 and then each carbon has to have 4 bonds: 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. And these would all have hydrogens for butane. This is the stuff that you would have in a butane cigarette lighter, the liquid. Now that's called a straight chain alkane because the carbons are in a straight chain. But they don't have to be in a straight chain. Nature provides all kinds of variations on this theme. And when there is a carbon-containing group coming off of the chain somewhere, we call that a branch. And we name it based on the backbone. Here is 4-carbon backbone, so that's a butane derivative. We call it a derivative. And here is the actual name for it. Here's butane at the end, saying there's 4 carbons in the long chain, in the straight chain, and it's 2-methylbutane. There are 2 pieces of information there. One is that the side chain, the branch, is a carbon with 1, 2, 3 hydrogens and, of course, 1 bond to the chain here. That's a methyl branch. And the other piece of information is this 2 here. And cleverly enough, the 2 tells you what carbon the branch is connected to. And we always make the branch connected to the lowest possible carbon. If we started on this other end, this would be 1, 2, 3 methylbutane. That's not as good as 1, 2 methylbutane. 2 methylbutane is better than the other. Okay? Now, functional groups, we're going to look at 3 of them. One is alcohols, in which instead of a methyl group here, we have an OH group. When you have that, the end of the name has OL. OL means alcohol of some kind. So this is 2-butanol. Butanol because there are 4 carbons. 2-butanol because the OH group that makes it an alcohol is connected to the 2nd carbon. You could have 1-butanol if the OH were here. You'd have to move a hydrogen over and get it out of the way. Okay? The second one, which we won't do much with, is amines, where instead of an OH group, we put an NH2 group. And this would be ethane amine here. It has an NH2 group in place of one of the carbons of ethane. Not too much, we won't do much about that. Something we will look at more frequently is a carboxylic acid. And the carboxylic acid is an organic compound that has on the end a carbon that has an oxygen with a double bond. I know we haven't talked about that yet, but it's an oxygen with a double bond and then an OH group. So if there were a hydrogen, just a hydrogen right there, that would be a 1-carbon organic acid. And the names of these things end in oic acid, O-I-C, acid. Now this is one with 1 carbon, so it's meth. Well, let me back up and make myself a little more room. Methanoic acid. Okay? We take the methane, we drop the E, and put oic acid on that. If there were a carbon out here, we had this carboxylic acid group connected to a carbon, we'd know how many hydrogens will be on this end. Going to be 3. So that's a 2-carbon acid, organic acid, carboxylic acid, and because it's 2-carbon, we would call it ethanoic acid. Ethanoic acid. Okay, ethanoic acid is something you encounter very frequently in vinegar. It's the substance that makes vinegar acidic. Ethanoic acid is a very common biologically important molecule. So if we looked at this long guy over here, what do you think the name of him would be? 1, 2, 3, 4, 5 carbons. 5 carbons, oic acid, pentanoic acid. Pentanoic acid. It smells like sweat socks. Bad sweat socks. Okay, I have one thing left to do and I have 2 minutes to do it. You have questions here. Question where? Yes, go ahead. I couldn't hardly hear you, but I think you asked about a methyl substitute. 2 2-methyl-butane. Oh, back a slide? Okay. Methyl is the, distinguishes the group as an attachment, a branch. So it would be methyl or ethyl or propyl. The YL ending means it's a branch. I'm sorry, I should have mentioned that. Okay, I'm going to skip one slide, and I'm going to go to this one. The last thing in the chapter has to do with calculating the molecular mass of a compound. Once you know how to connect the name to the formula, you take the name, you make the formula, and you multiply the number of atoms of each type by its atomic mass and find the sum. So that will give you the molecular mass. So if we look at this compound, I said there were a lot of phosphorus sulfides. Here's one of them, tetraphosphorus trisulfide, P4S3. If I wanted to know the formula mass for this thing, I would take the atomic mass of phosphorus multiplied by 4 plus the atomic mass of sulfur multiplied by 3 and sum them. So here is the form, here is the number, here is the result, 220.1 AMUs per formula.